All right, now we're going to do a really complicated kind of chain rule problem so that you can see one with many more variables. And so we're going to try to find dw ds if w is equal to 4x plus y squared plus z cubed, and x is equal to e to the rs squared, y is equal to ln of r plus s over t, and z is equal to rst squared. And I'm going to show less of the work in explaining this time so that we can get through this more quickly, because we're going to have more layers to think about. And we're going to go ahead and say that this one has to only be in terms of r, s, and t. To do that optional step I described last time about needing to use only the lowest level variables. So I'm looking for dw ds. So the variable on top is where I start. There's my w. And I have to write everything it depends on. So w is 4x squared. It's got an x. Plus y squared. It's got a y. Plus z cubed. So it depends on z. And then for each x, y, and z, I have to write the relationship for the variables it depends on, which x depends on r and s. Y depends on r, s, and t. And z depends on r, s, and t squared. Sorry, r, s, and t again. And so hopefully you can see that I am bad at judging the space that things will take up, but I did try to keep this on there's a level, there's a level, there's a level. And what I'm trying to find is dw ds. So I'm eventually going to want to end down here at all of my s's. And I know last time I took the derivatives as I went, but that's because it was really simple. If we look at this map, there's a lot of lines that maybe I won't necessarily have to go through to reach these s's. So I'm going to highlight my paths first and then take my derivatives. So to reach this s, I can go down through x to get down to s. That's the only way to reach it. To reach this s, I go down through y and then down to s. And to reach this s, I go down through z and then down to s. And so the paths that I follow are for the dw dz, dw dy, and dw dx at the first level, w to x, w to y, w to z, and then from x to s, dx ds. I'm using that soft-sided d because x depends on more than one thing. And then I used dy ds and dz ds. And so my paths are dw dx times dx ds, dw dy times dy ds, and dw dz times dz ds. But I know that I just have to multiply down all my paths and then add them all up at the end. So if I want to find dw ds, I know it's just the sum of those three products. And this is going to be my formula that I use to try and find the answer to this problem. And I worked this one in this kind of more truncated form that only shows what I actually need, sort of to model how you might want to do it on an exam. You don't want to do it this painstaking way I did every time. Once you get the hang of it, you can kind of show a little bit less work for how you get to this point. And so I just need to fill in each of these partial derivatives and then I'm done. So I was given w. So I know dw dx is 4. dw dy is 2y. And dw dz is 3z squared. Even though we had a more complicated map, balances out with some easier derivatives this time around. And then I'm going to need dx ds. So the derivative of e to the rs squared. My exponentials kind of always stay the same, and then pull the derivative out front. So that becomes 2s times r. Just a chain rule for a function of one variable, really. We're treating r like a constant for this partial derivative. I know we're struggling with getting the hang of that. And then dy ds. See, I've got a natural log, so I know I'm going to want to put in the bottom whatever was inside the natural log. And then on top, I put the partial derivative of the argument to the natural log with respect to s, but that's just 1. So that's going to be t over r plus s when I simplify by just moving that t up top. And then my dw dz, it's that I want dz ds. Z was rst squared, so the partial derivative is just 2. Oh no, made a mistake. I'm taking the partial with respect to s, so it's just rt squared. And then I can just plug everything in. I can say, okay, dw ds was dw dx, that's 4, times dx ds, that's 2rs e to the rs squared, plus dw dy, that was 2y, times dy ds, that was t over r plus s, plus dw dz, that was 3z squared, times dz ds, that was rt squared. Now I've gone ahead and I've taken my formula for the chain rule and I've plugged in all my partial derivatives. But we have to find our answer in terms of r, s, and t. So we're going to do that optional last step of anywhere I have intermediate variables, that's stuff that wasn't my top variable or my bottom variable, I have to replace them in terms of things that are in the bottom row. So my 4 times 2rs is fine. I'm going to go ahead and just simplify that while I'm here. And then my 2y, y is in that middle row, so I have to replace it with something that depends only on r, s, and t. So that's this equation right here. And then just keep everything else the same in that term. And then my 3z squared, I'm going to have to replace z with something that belongs to the bottom row. That's r, s, and t. So I just go ahead and plug in that r, s, t squared squared rt squared. And you could go ahead and simplify this, I guess. I'm not going to because there's not room on this page. So we're just going to call that our answer, and I'm not even going to draw a box around it because that box will be very uneven. You're just going to have to accept that this is the answer. I'll do brackets. There. So that's our answer with the simplified version where we plug in R, S, and T for a pretty complicated map for the chain rule. So hopefully you've seen sort of the easy example to get familiar with it, and then this tougher example that prepares you for some of the more difficult ones you might have to build.